Bond angles are the angles formed by three bonded or adjacent atoms. The number of charge clouds around the central atom, which is the apex of the bond angle, determines the bond angles. If an atom has two charge clouds, these charge clouds will orient in a bond angle of 180 degrees to get as far apart as possible. There's a Lewis dot structure of carbon dioxide on the slide where the central atom carbon has a double bond to each outer oxygen atom. Since there are no lone pairs on the carbon atom, the total number of charge clouds is 2 since there are two outer atoms. Carbon dioxide is actually a linear molecule with a bond angle of 180 degrees. If an atom has three charge clouds, these clouds will orient to 120 degrees to be as far apart as possible. On this slide is the Lewis dot structure of boron trifluoride and germanium difluoride, neither of which follow the octet rule. In boron trifluoride, boron has three outer atoms and no lone pairs, so it has three charge clouds, while as germanium difluoride has two outer atoms and one lone pair for a total of three charge clouds. The bond angles are 120 degrees, but in germanium difluoride this bond angle is actually slightly less than 120 degrees because lone pair electrons tend to take up more room and repel more than bonding electrons. So if two charge clouds are 180 degrees apart and three charge clouds are 120 degrees apart, what is the angle for four charge clouds? You may have thought 90 degrees. And if a molecule had to remain in two dimensions, that would be the case. However, molecules exist in three-dimensional space and thus have the larger angle of 109.5 degrees when there are four charge clouds around a central atom. This slide shows the Lewis dot structure of methane, phosphorus trifluoride, and hydrogen sulfide. Each central atom has four charge clouds. The carbon in methane has four outer atoms. The phosphorus in phosphorus trifluoride has three outer atoms and one lone pair. And the sulfur in hydrogen sulfide has two outer atoms and two lone pairs. All of the bond angles are approximately 109.5, although if the central atom has a lone pair, then those bond angles are slightly less than 109.5 due to the higher repulsion of lone pair electrons. The Lewis dot structure for methane shows wedges that represent the three-dimensional nature of the 109.5 bond angle. The solid lines represent bonds that are in the plane of the paper or the screen, while the solid wedge represents a bond that is coming towards you from the screen, and the hatched wedge represents a bond that is behind the plane of the screen or paper. This ball and stick model of methane shows these angles. If these two bonds are in the plane of the screen or the paper, this bond would be the solid wedge which comes out towards you from the plane of the paper or screen, whereas this bond would be the hatched wedge which goes behind the plane of the paper or the screen. Any bond angle on this model is going to be 109.5.